Bueno, muy buenas tardes. Tengan todos ustedes bienvenidos a la sesión de la plenaria de dinámica de fluidos. Mi nombre es Enrique Guzmán, actual vicepresidente de la División de Dinámica de Fluidos, y hablo a nombre de la doctora Rosana Bonacía, nuestra presidenta, para hacer la presentación en inglés de nuestro invitado, el profesor Christopher Brennen. Antes de hacer la presentación en inglés, quiero recordarle a todos los asistentes que pueden, por supuesto, hacer las preguntas que crean pertinentes a través del chat. Pueden escribirlas en español o en inglés y con gusto se las haremos llegar al profesor Brennen para que las conteste al final de la sesión. Bien, entonces, good afternoon. Welcome everybody to this plenary talk on fluid dynamics. My name is Enrique Guzmán, and on behalf of the President of the Fluid Dynamics Division, Dr. Rosana Bonacía, it is my real honor to introduce our distinguished speaker, Professor Christopher Brennen. Professor Brennen attended Oxford University, where he earned his bachelor, master, and doctor of philosophy degrees. After graduating, he became a junior research fellow at the National Physical Laboratory in the UK, and then he became a Fulbright scholar. He was a member of the mechanical engineering faculty at the California Institute of Technology for over 40 years, after which he retired as the Heyman Professor Emeritus of Mechanical Engineering in 2005. There, he was a Master of Student Houses, Dean of Students, Executive Officer, Department Chair of Mechanical Engineering, and Vice President for Student Affairs. As a teacher, he was a recipient of a number of teaching awards, including the prestigious Richard Feynman Prize. Throughout his career, he has received several awards for his contributions to the field. Just to mention a few, he won twice the Robert Knapp Award for the best paper, the ASME Fluids Engineering Division, the NASA New Technology Award, the ASME Centennial Medallion. He was the first non-Japanese recipient of the Fluids Engineering Award of the Japan Society of Mechanical Engineers, and he was also the first non-Japanese recipient of the Fluid Science Award from the Fluid Science Foundation of Japan. He's the author of over 260 scientific papers on 4 sole authored books. These are Hydrodynamics of Pumps, Cavitation and Bubble Dynamics, Fundamentals of Multiphase Flow, and Thermohydraulics of Nuclear Reactors, all of which are currently published by Cambridge University Press. The first book has been translated into Japanese, Chinese, and Farsi, while the second has been translated into Chinese. He's also the author of popular internet guides to the sport of canyoneering. Professor Brennen has also served as a consultant to numerous companies and agencies, including the United Nations, NASA, the US Navy, the Nuclear Regulatory Commission, Brookhaven National Lab, Lawrence Livermore Lab, Battelle, IBM, Rockwell International, McDonnell Douglas Aerospace Corporation, Allied Signal, General Dynamics, General Electric, and so forth. Today, he will be talking about the fascinating process of cavitation in medicine. Professor Brennen, welcome.
Thank you, Enrique. Can you hear me?
Yes, we can. And
can you see me?
We can see your presentation, Professor.
No, okay, so you can't see me.
We can.
All right. Just one moment. Let me get this started. Thank you, Enrique. Can you see my presentation?
We can, Professor, yes.
What I'd like to do today is to talk about cavitation and some of the basic processes in cavitation, which, as most of you know, is the formation of vapor bubbles in a liquid or other medium when the vapor pressure falls below, the vapor pressure. It is a dramatic phenomenon because it can cause great damage to nearby surfaces in which it occurs. I'm going to start just by a couple of notes. I want to say that a lot of what I'm going to talk about owes a lot to the colleagues that I've collaborated with over the years. And in particular, I want to draw attention to Alan Acosta, who was my mentor and friend for many, many years. He passed away about a month ago. So the cavitation community is sadder as a result. Can you still see me, Enrique?
Yes, Professor, we can.
Okay. Just wanted to check. So what I'll do is talk a little bit about some of the phenomena that we have uncovered in our research on cavitation for the first half of my talk. And then in the second half, show how that knowledge is being utilized to good effect in the field of medicine. And there are some remarkable processes that are emerging from those applications. To begin with, a little bit of history, just to set the scene. Cavitation was first recognized as an engineering problem back in the 1890s when a new high-speed propeller was installed in a Royal Navy vessel by the name of Daring. That what happened was that it was supposed to, it didn't perform the way it was supposed to perform. And moreover, the new fast propeller made a great deal of noise. And it wasn't long before the engineers recognized that that noise was accompanied by damage to the material surface of the propeller. Sir Charles Parsons, who was involved in that process, also did experiments with his own vessel, shown here, the Turbinia. Well, since then, we now know that when the cavitation bubbles collapse near material surfaces, they generate extraordinary damage, even in quite hard metals. This is an example. This is a Francis turbine runner, which has experienced cavitation. And you can see that the cavitation has eaten through, almost completely eaten through the turbine runner blades. And they're made of cast iron in this instance. You'll notice that it has a crystalline like appearance, this damage, and I'll make reference to that again a little later. My favorite example of cavitation damage arose during the year 1983, when the Colorado River experienced a huge runoff, unusually large. The dam level rose to a point where, for the first and only time, the water overflowed into this spillway and then this trench, and then went down this tunnel, which is about 30 feet across, to join the river downstream of the dam. Well, we happened to be there on this camping trip with two of my children and witnessed this overflow. And it was quite remarkable, an extraordinary roaring noise. And the violence of the flow was so great that it rained in a radius of about a quarter of a mile around this location. A little later on, when the overflow ceased, they did examine this large pipe that led to that carried the outflow down to the downstream of the dam, and they were alarmed to find this huge hole dug in the pipe. It was about 30 feet long, about 20 feet wide, and about 15 feet deep. And by way of scale, notice a man here standing next to that. The damage was even greater on the Glen Canyon Dam, which is upstream of the Hoover Dam. And there, the damage was very close to destroying the dam itself, which would have had catastrophic consequences. All right, so damage is a big problem. It's not the only one, but jumping back in time again, Robert Knapp, who was a professor at Caltech, was interested in doing some of the first experiments on cavitation in a high-speed water tunnel, which he constructed. Knapp was working with Theodore von Karman, who had taken over kind of the leadership of fluid mechanics research at Caltech. And here you can see the upper leg of the tunnel, and this is the working section in which a model would be installed. It would have a low pressure region on the surface of that flow, which would cavitate. And I'm going to show you a rather unique video, the very first movie of cavitation taken by Robert Knapp. Hopefully you can see this. Here the flow is from the right to the left. You can see the bubbles are growing and collapsing. The bubbles, and one of the things that you see from these high-speed movies is that they originate with small, what we call small bubbles that exist in this flow. And almost all water in a water tunnel or in the ocean has these small cavitation nuclei that seed the cavitation. The other thing that you can see here is that these bubbles grow fairly explosively, but then they collapse even more violently. And if you focus on this region here, you can see the bubbles collapse and the cloud of small bubbles that's generated as a result. All right, the nuclei tend to be between about 5 microns and 200 microns in size. Larger bubbles or nuclei settle out and so are inconsequential. Smaller nuclei are stabilized by cavitation. So those are the sizes, that's the starting size for the bubbles that occur in cavitation. About the same time, back in at the beginning of the 1900s, Lord Rayleigh was interested in this phenomenon and came up with an equation to model the growth of bubbles. Later on, that was augmented by my colleague Milton Plessett, and jointly now they're the equation for a spherical bubble. And I want to emphasize the spherical bubble. Was known as the Rayleigh-Plessett equation, and it relates the size of the bubble R and its time derivatives, as a second time derivative and first time derivative, to the pressure difference between the pressure inside the bubble, which is comprised of a vapor pressure plus a pressure due to the residual small amount of contaminant air in the bubble, and the pressure far from the bubble. Now, if you look at this, this is a highly nonlinear equation, and it results in quite extraordinary dynamics. Here we've calculated the results of this for a nucleus that passes through a low pressure region between here and here. The growth is fairly, though explosive, fairly gradual in comparison with the collapse, which is extremely violent. The surface of the bubble rushes in at high speed to this first collapse. And it collapses to a size very much smaller than it had at the start. The result of that is a very violent process in this collapse, which produces noise and shock waves. It produces damage when that bubble collapses close to a nearby surface. And the small amount of air in that bubble is compressed to such a high extent that it reaches very high temperatures and pressures, and flashes of light are emitted in a process known as sonoluminescence. There may be later collapses. I'll come to that in a moment or two. Well, a couple of other features to highlight. This is a graph of the volume of the bubble as it reaches that very tiny collapse size. It therefore has a very large second derivative of the volume of the spectra time. And now the noise that's generated by this process is proportional to that second derivative. And so that's why you get a large positive spike in the acoustic pressure as a result of a collapse of a cavitation bubble. This is the density of the fluid. This is the distance of the measurement from the collapsing bubble. Now, some years ago, a student of mine, Stephen Ciccio, and I decided to try to measure the noise from a single isolated cavitation bubble. Isolated because you don't want it contaminated with the reflection of that sound from the surrounding walls, other bubbles, etc. We were able to do that. I won't go into the details, but this is what you find from the noise when you do that. A very large positive spike. Then it's followed by some noise I'm not sure I completely understand. And then this is from a second collapse. We identify the magnitude of that collapse by the area under this first spike, and that's called the acoustic impulse. And I'm plotting here the acoustic impulses from the Rayleigh-Plessett equation with experimental measurements. All of these are different experiments, different sizes of bubbles and different nuclei, etc. Notice that there is about an order of magnitude difference between the Rayleigh-Plessett calculation and the upper limit or upper bound of the experimental measurements. And that's because when you look at what happens when these bubbles collapse, they don't maintain their sphericity. They deviate from the spherical shape. That lessens the focusing of the shock in the center of the collapse. And so you get substantially less noise as a result, but it's still substantial. Moreover, each of these curves goes up and then comes down, and we were able to demonstrate that that's a result again of the larger bubbles in this range here on the, having deviating more readily from the spherical shape. So we understand something of the energy, acoustic energy generated by a single bubble collapse. And indeed, there were more details that were added. Albert Ellis also worked in the same lab with Milton Plessett and others, and he was a remarkable man. He developed the movie camera and the still camera that took the pictures of cavitation. This was his entire invention, and it's still a camera design which is used today. This is a typical photograph of a single collapsing bubble that Ellis took, collapsing close to a wall. And what happens when a bubble collapses next to a wall is that the side further away from the wall collapses in most rapidly, creating a re-entrant jet, which achieves very high speeds and impacts the other side of the bubble wall and the wall with a shock, a substantial shock. Now, in a region where cavitation is collapsing, it follows that the surface of that nearby is continually hammered by these collapsing re-entrant jets. Maybe that was an early explanation where people argued that this continuous hammering of the surface by these jets led to fatigue failure of the surface. The material flaked off, and these jets then started to work on the layer of material underneath that flake. However, there's more. Oh, I should show this picture. This shows, this is a movie from my friend Shenkai Li, showing you a bubble collapsing. You can see the violence of the jet directed at the wall. And you can also incidentally see here that the result of the collapse is a little cloud of bubbles, a micro cloud of bubbles. And I'll show you, I'm going to talk in a moment or two about the consequences of that. Here's a microcloud from another study of the single bubble collapse. But clouds of cavitation bubbles are also a part of many cavitating flows. This is the cavitation of a model of the liquid oxygen pump in the Space Shuttle main engine. The main flow is from the right to the left, and you can see these clouds are continually formed and collapsing. And that's what makes this noise flow particularly noisy. Professor Gorham Bark performed the following experiment. He painted this propeller with a red paint, which would be easily eroded, and then put it in the water tunnel and allowed it to cavitate. And if you look carefully at this movie, you'll see that the cavitation clouds are collapsing right precisely where the paint has been eroded from the surface of the propeller blade. There's a one-to-one correspondence of those. So that shows you that these collapsing clouds are particularly damaging in cavitating flows. So that motivated us a few years ago, a couple of students, Luca D'Agostino, Jack Wang, to set up a calculation of how a cloud of bubbles rather than a single bubble would collapse. Here's and we chose a spherical cloud because it would be the simplest to model. A cloud of radius A, bubbles of radius R, surrounded by pure liquid. And then what we did was ask what will happen to this in this multi-phase flow if you lower the pressure far away from this cloud and then increase it again. And what happens is what you might expect. The bubbles on the surface of the cloud collapse first. And that creates a kind of a propagating collapse wave, which moves inward. And I'm going to show you one numerical result from one of those calculations. This is a point in time where that collapse wave has moved into about a half the radius, original radius of the cloud. And the black line are the size of the bubbles at the various locations at that moment in time as a function of radial position. So the bubbles further out, for larger radii, have collapsed. The bubbles in the interior have not. You notice this becomes, in fact, not just a collapse front, but a shock wave. And this shock wave has a structure that looks very similar to the calculations of the Rayleigh-Plesset equation. Not only is there this propagating shock wave, but associated with it is a very high pressure pulse. This red line is the pressure pulse at this time. And as the shock moves further into the center of the cloud, that peak, the acoustic impulse, if you like, gets larger and larger, so that when it reaches the center, when it's focused in the center, you get a huge pressure pulse as a result. Now that means that not only does a single bubble have produce shock waves that might generate damage, but much larger shock waves are generated by clouds. All right, so I want to show you an experiment now that we did to try to shed a little more light on this, because most cavitation clouds aren't spherical. And so what we did was we installed a hydrofoil in the water tunnel, which we oscillated in pitch. And so each pitch oscillation, it generates a cloud of cavitation bubbles which then collapse. Now I have to tell you that when we ran this experiment in the lab, this experiment, it shook the whole building. It was like a machine gun going off. Extraordinary amount of vibration and noise as a result of these collapsing cavitation clouds. So the question is, what did we find out about the nature of those shock waves generated? And so what we did was we installed flush-mounted pressure transducers in the foil and one on the wall, and then we ran the experiment. Now I have to be honest with you and tell you, the first time, these are quite expensive transducers, and the first time we ran it, we destroyed the whole set within a matter of seconds. Well, we solved that by figuring out a way to kind of shield them a little bit from the worst of the cavitation shocks, and then conducted the following experiment. We would set up the vibration, and then we would allow the signal from one of these transducers to take a high-speed picture of the cavitation at that moment in time. So here's a typical picture. This is a moment in time when this pressure transducer, which you can now see, you can see it through the cavitation. You can see it through it because here the bubbles have collapsed completely. So the cloud has become transparent. And this is the structure which is just passed over that transducer and generated the noise. So this is the shock wave. Now that's about all we can say. We can say the magnitude of the shocks. I cannot really explain to you why they take this kind of shape, but it does, this crescent shape. We can't really tell you what these structures are in the inside, though they're probably vortices of some kind. But what we can say is that even in this very different geometric shape, these cavitation clouds produce very large shock waves, which may be responsible for the damage caused in many cavitating flows. All right, so with that in background, in other words, we have damage from single bubbles or damage from collapsing clouds. I'm going to talk now about some of the important medical contexts. I'm going to first talk about unintended cavitation damage caused by cavitation that you don't really want to happen in a medical context. Then I'll talk about deliberate cavitation damage. And then finally, about perhaps the most exciting recent development, the micromanipulation, the treatments using cavitation. First of all, the unintended cavitation damage. The one I'm most familiar with is heart valve cavitation. Heart valves do cavitate somewhat. Artificial heart valves cavitate a lot. And that's been a significant problem, because the cavitation in artificial heart valves, and I'll show you there's a whole range of designs, causes not only damage to the valve itself, though that's a relatively minor issue, but also that they destroy red blood cells at sometimes an unacceptable rate. Let me show you why. I'm going to focus a little bit on a bileaflet valve, St. Jude valve, because I have a movie on that. Here's what happens in a heart valve, and this is a bileaflet valve. The forward flow, these are the valve leaflets, which, when the forward flow occurs, are oriented in line with the flow, and therefore there isn't much disturbance due to the leaflets. Now, at the end of the diastolic phase, when the flow reverses, those leaflets are folded back, and just before they close completely, there's a very high-speed jet that is projected upstream by the pressure difference, and because there's a low pressure in behind. See that this fluid that's now moving to the left generates a low pressure in this region when it's stopped. I'm going to show you a little bit of film of that, of what happens. This is looking at this bileaflet valve from downstream, and I'm repeating it many times here. And you see these clouds of bubbles that are generated at the very last moment of closure. That's difficult to deal with in terms of the blood damage to the red blood cells. Human hearts are flexible. This material is not flexible. When it's flexible, the collapse is much less, the closure is much less violent and much less damage. And so that's why the pig valves, for example, are still preferred to these solid surface valves. We're not very good, really, at designing structures like this with flexible materials, and that remains a problem and an issue. All right, so what are some of the problems? To understand this, there are several things you need to understand, follow. First of all, what are the nuclei number distributions in blood? As far as I know, no one has measured them. And in order to quantify cavitation in any context, you need to know the nuclei number distributions. Secondly, this cavitation depends upon the coincidence of nuclei in the regions of instantaneous low pressure. And that's hard to model and hard to completely quantify. Moreover, thirdly, both the nuclei number and the testing system are different usually from that in the body. And so you have to factor in the different system dynamics in understanding the flow, the tests in the laboratory. Very briefly, artificial hearts are even harder to understand. They typically have this kind of structure. This is the DeBakey heart with an impeller that looks very much like that space shuttle impeller that I showed you. And the problems there are even more complex, as you might imagine, than in the heart valves. All right, very quickly, let me mention a couple of other circumstances where unwanted cavitation occurs. Head injuries. This cranium that you have, this vessel filled with liquid, when it is bangs on a solid surface, generates pressure waves which bounce around in your skull and creates nodes and antinodes, where the pressure is low and cavitation occurs. And it's reckoned that when it does occur, the damage caused by the cavitation, which might be in a quite different location than the impact point, is much greater than the damage from the impact in the impact zone. All right, well, let's get to pleasanter things, some of the more deliberate cavitation damage and how it's used to beneficial effects. The most obvious and most common use of cavitation in medical context is in ultrasound cleaning. But when you go to the dentist these days uses a probe which vibrates, and they call it ultrasound. But that ultrasound is not what cleans your teeth. What cleans your teeth is the cavitation caused by the ultrasound. So that's very common and almost universal process for teeth cleaning. It's also used in a much larger scale, for example, to clean the hulls of ships. But more interesting in some ways is the second listed item, phacoemulsification. That's the process by which in cataract surgery, the old eye lens in the eye is removed by the insertion of a tool from the side which vibrates. And that vibration, at ultrasonic frequencies, emulsifies the material of the old lens and allows it to be suctioned out. This is now a very common procedure used in cataract surgery. Here's an interesting video given to me by Dr. Aziz Aniz of that probe in action. And this is cavitation, which is emulsifying this surface. Dr. Aniz also provided me with a measurement, a recording of the pressure in the eye socket when the phacoemulsification is going on. And if you look at this signal here, you'll see that this is caused by the cavitation, and it's almost identical to the form of the signal I showed you earlier from a single cavitation. So phacoemulsification is an important application of cavitation, and it's one of the most common surgeries ever conducted. All right, it's getting a little more sophisticated, and this is a gradually increasingly sophisticated list. Lithotripsy by shock waves. This has been a procedure that's been in place for a long time, where you submerge the human being in a bath of water. The bath is provided with what's called a lithotripter, in which shock waves are generated at this one focus, and those shock waves are focused. Second point, in the kidney or gallbladder or whatever, in order to fracture the stone that might be present, so that the pieces of that stone can then be flushed out by natural processes. All right, that's all right. And here's some examples of artificial stone damaged by cavitation. Here's another example of the cavitation in shockwave lithotripsy on a target stone. Here the problem in the lab, here the problem begins to be clear. You see these bubbles aren't on the surface. And what that does when they collapse is it damages the surrounding tissue. So one of the problems with shockwave lithotripsy is what they call collateral damage. Here's another example of a stone with bubbles which are presumably damaging the surrounding tissue. But it's also possible to get around that. And my friend Yoi Matsumoto at the University of Tokyo and others have pioneered the process of using ultrasound for lithotripsy rather than shockwaves. And the advantage of ultrasound, particular single frequency is you can focus that much more precisely and therefore minimize the collateral damage. Here is a stone being damaged by ultrasound. The other advantage of that ultrasound is shown here. Matsumoto has devised various strategies in which he uses a very low amplitude ultrasound to create a cloud of bubbles by what's called rectified diffusion. And then he hits that with a much stronger amplitude wave, which collapses the cloud. That's a kind of strategy that's possible with ultrasound, but not with shock waves. Laser surgery, very briefly, I'll mention that. And there's some others here, but laser surgery is an interesting one because it's possible to make very small incisions with a focused laser. Vogel and Bush showed that picosecond pulses provide a better cut than nanosecond pulses shown here. However, I think the most fascinating modern development is in the micromanipulation of nuclei in treatments, in medical treatments. And these treatments almost all use what we call microbubble contrast, just contrast agents. A contrast agent is a suspension of tiny stabilized microbubbles. And the intention is to do the following. To put them in the bloodstream or elsewhere, and when they get close to cells you want to destroy, let's say cancer cells, you then hit it with focused ultrasound, and these little bubbles then explode and destroy the cancer cells. So that's a very neat thing to do. And it turns out, and people have done studies of these processes, all the details. Here's a human cell, for example, which shows the pits generated by a re-entry jet. But that's not by any means all of it, because they've also used similar techniques to deliver drugs in locations where they need to deposit them. And for that purpose, you use very special nuclei, which are carefully constructed. And they're called liposomes, and so this is a typical cavitation nuclear contrast agent. It consists of gas in the middle, and when you hit it with the ultrasound, that explodes the whole thing. Drugs are then installed in the oil layer around that gas, and it's covered over in a lipid layer in order to stabilize it. Then ligands may be attached to it, which preferentially attach also to the target. There's more than this. This is complicated. People are manufacturing these special contrast agents like crazy with all kinds of properties, which I show here, many different variations of these liposomes, custom microbubbles, if you will. In addition, for example, others have installed, including Eleanor Stride at Oxford, have installed magnetic particles in the layer around this bubble so that you could guide them to the location where you need to deploy them. And that's not the final word either. Here's a process of injecting new DNA into living cells where you take the microbubble, cationic microbubble, you bring it near to the cell where you want to inject the DNA, and then you hit it with the ultrasound so that the new DNA gets installed in the cell. Remarkable. It seems like impossible, but it's not. Of course, you have to do things like you have to make sure when the cavitation bubbles collapse near that cell, that the cell continues to live. And there's some quite a bit of research on that. I'm using this as an example in which a skeletal muscle cell has been hit with a cavitation, creating a reinterjet hole, and it wasn't strong enough to destroy the cell, and it healed over. So it's possible to inject stuff into cells without destroying the cells. Well, let me indicate some key research issues for cavitation in biology. First of all, nucleation sites, their existence and control. It's hard to measure them. Measuring them in blood is not easy. But it's essential in order to quantify and know what is going on. Transient unsteady cavities, the processes we're talking about are mostly transient and unsteady. And so you have to address the issue of the coincidence of nuclei and low pressure regions. Transient unsteady cavity, the role played by structural flexibility in determining cavitation occurrence and cavitation damage. Very important in determining what goes on. We also don't really know a great deal about the cavitation responses of these coated nuclei. I mean, that's critical in order to be able to adjust the processes so that the cells are not damaged beyond repair. And how to position and control the cavitation nuclei are obviously important. In summary, it seems to me there's huge potential for the highly focused remote deposition of energy for the removal of reduction of tissue. There aren't many processes that allow you to focus energy in this way. And there are a multitude of these applications. There's obviously an increased need for understanding of cavitation in the biological context in order to reduce the collateral damage and to enhance the life of devices such as artificial hearts and heart valves. Clearly, there's enormous potential for the manipulation of cells using cavitation, using contrast agents or cavitation nuclei. So on that note, I'll stop and take any questions that you wish. Thank you for your attention.
Thank you very much, Professor Brennen. You can switch on your camera so that people can see you.
All right. I'm not sure quite. I'm not sure why I haven't done that. Usually it comes on automatically, but I will attempt to do that.
On the lower left corner, you should find a button, I think.
Lower left corner, you should find a button. Let's see.
In the meantime, we are expecting the questions to
Of course. You can proceed. I'll try and get the camera working very soon. Usually it comes on automatically. Let me do that.
A nuestros invitados.
I see. I think I got it now. Yes. So finally you can see me. Sorry that I didn't do that earlier, but I think you can see me now, right?
A nuestros invitados, si quieren hacer preguntas, ahora es el momento. Pueden hacerlas en español, por supuesto. Yo trataré de traducir para el profesor Brennen. There is one question, Professor. What is your forecast about the development of future technologies evolving around these cavitation processes in medicine, such as, for example, small-scale applications involving labs on a chip, micromachines, nanotechnology, and so forth?
Yeah, that's a pretty broad question, but obviously what I've talked about today implies a considerable expansion of the use of these contrast agents in medical treatments. It seems almost limitless what you could do if you can control these nuclei, cavitation nuclei, and put them where you want them in the body without remotely without incisions in the body. So I think that's a huge potential injury industry, producing these contrast agents and developing them. So that's one. Cavitation is also used in many other technical circumstances. For example, in peening of metal surfaces, it's used in cleaning, as I've said. And there are many circumstances where cavitation is used for cleaning off surfaces. So it's got a tremendous potential for use, and I think you'll see that those uses being expanded tremendously in the years ahead.
Okay, there is another question just arrived. We did not see any CFD simulations for the cavitation applications you presented. Is there any limitation on the use of CFD to simulate cavitation? This is a question posed by...
Yes, that's a very good question. And the answer is yes. The reason you haven't seen much, we have done simulations, but the problem is the multi-scale nature of cavitation. You're not only dealing with very small elements in the flow, these nuclei, in a much larger scale flow, but you're also dealing with different time scales, a very rapid scale of growth and collapse of the bubbles, and the smaller scale of the flow. So overcoming those multi-scale hurdles is a real problem. There has been significant advance. For example, my colleague, Professor Tim Colonius, has done some very nice work on multi-scale models of cavitating flows. But it's a real challenge to do that. And I think I'll leave it to him to tell you about that at some point in the future.
Thank you, Professor. There is another question by Lorena Romero. Have you modeled these cavitation processes coupling any cross effects like such as thermal gradients?
No, another good question. Again, that increases the complexity of the flow. I mean, you're dealing with a multi-phase flow, even at the best of times, with those two multi-scale features. And so when you add in other things like thermal gradients, like effects of various chemicals and surface reagents to it, it's hard to make progress when you get too many complications. There needs to be, in addition, significant new development of instrumentation to make the measurements you really want to know in these cavitating flows. Not only do the measurements have to discern small rapid time differences, but also scales, but also they have to survive in this intensely difficult environment of a cavitating flow. So that's another feature in making progress with the basic information.
Okay, so thank you, Professor. There is another question. How does tuning modulate the cavitation intensity could improve the valve design?
Tell me that again. Repeat the question, if you would.
The question literally says, how does tuning the cavitation intensity could improve the valve design? I guess he's trying to ask how can you modulate or tune the cavitation intensity to improve the valve design, or can it be incorporated?
I mean, certainly when you generate acoustic cavitation, the frequencies and the amplitudes can be tuned for various purposes. I did mention what Matsumoto does with with ultrasound damage. So yeah, those are certainly ways to tune the cavitation to achieve whatever you want to achieve with the cavitation by changing the frequencies. Almost all of the frequencies that are used are ultrasound frequencies in the range from 5 kilohertz up to 100 kilohertz. That's the usual kind of range that's explored. So you have that. And then the amplitude of the wave, obviously, is going to influence its effects. Cavitation is also highly nonlinear. And so whenever you use ultrasound, the nonlinearities show up. There are nonlinearities that affect a cloud, as well as, for example, the calculations I showed of a collapsing cloud. My former student, Jack Wang, has also explored what happens when you use various frequencies of excitation to modulate the behavior of the cloud. So yes, there are lots of things you can do to tailor the process.
Okay, so thank you, Miguel Mayorga, for the question. We have another question from Lorena Romero. She says, out of curiosity, could you explain a little bit more about how do you experimentally followed the individual bubbles?
Oh, yes, I see. Yeah, those experiments were done by my former student, Stephen CCO, who's now at the University of Michigan. What we did there was we deaerate the water so that the number of nuclei entering the region of cavitation is very small. And then we kind of try to pick off the individual bubbles that come through that region. What CCO did was devise a way of detecting the approach of an individual small bubble, and then using that detection system to trigger a camera to take pictures of that a single bubble and look to see both how it evolved as it went through the low pressure region, but also to understand the noise that it produced. And there are some very interesting microfluid mechanics associated with those observations.
Okay. Quiero recordar a todo el mundo que también pueden preguntar en español si desean. We have time for a couple of questions if you want.
Sure.
There is another question here. Do you think, Professor, that the focused energy produced during the collapse of the bubbles can be harnessed somehow for certain applications?
Well, I mean, that's what I've talked about. It is harnessed in most of the applications that I described. If you mean extracted from the flow, I don't see much chance of doing that. This energy that's focused only persists for a very brief length of time. So the actual magnitude of the amount of energy generated is very small. It's highly focused, and that's why cavitation is so useful. But its magnitude is not big.
Okay, so in a large scale, this would not be feasible, perhaps. Okay, there is another question by Ricardo Jara Jimenez. Is there any application of cavitation in the topic of virology?
Of virology, of viruses, you mean?
I presume he's referring to viruses, yes.
Right. I don't offhand know of such, but there may be. Clearly, if you could devise a cavitation bubble that would attack a virus, that would be an extraordinarily valuable development. I don't know of any. I suppose it's conceivable, but I don't know of any.
Okay, thank you very much. Any other questions? ¿Alguna otra pregunta? Okay, I think that's all. Very well. There is another one coming in. Yes. This might be a little bit complicated. Is cavitation phenomena does behave similarly in low gravitation environments? This is a question by Ricardo Ochoa.
Yeah, I don't think gravitational forces really have much to do with much effect on cavitation. So I think it would behave very similarly in the space shuttle in Earth orbit as it would on the surface of the Earth. There are some, there are some minor gravitational effects that you can observe in cavitating flows, but not in the kind of flows that I discussed in this lecture.
Okay. There is one comment by Lorena Romero. She wants to thank you for this enlightening lecture, Professor, and we all do. Thank you so much for your talk. It was a real pleasure listening.
Thank you, Enrique. Thank you for your help as we got through it. Thank you.
Okay, and we look forward to having you again sometime.
Thank you very much. Thank you.
Thank you so much. Goodbye.